Well, the universe as we know it has a beginning. We call this origin story the Big Bang. It was not an explosion in space, not a firecracker in a dark room. Instead, it was the very beginning of space itself, and of time. About 13.8 billion years ago, everything was compressed into a point of unimaginable density and heat, a state we call a singularity. In a tiny fraction of a second, it began to expand, not into anything, but as the fabric of existence itself stretching outward. That initial, violent expansion set the stage for everything to follow, in conditions so extreme that known physics may not fully apply. The early universe was an opaque, searing plasma, a cosmic soup of protons, neutrons, and electrons, forming and annihilating in a frenzy. Light, photons, could not travel far. They were trapped, scattering off a dense crowd of charged particles. As space expanded, energy spread out and temperature fell. Cooling transformed chaos into the possibility of structure. Around 380,000 years after the Big Bang, at about 3,000 Kelvin, electrons were captured by nuclei. Neutral atoms formed, mostly hydrogen, with a bit of helium. With electrons bound, the universe became transparent. For the first time, light could travel unimpeded across space. We detect that ancient light today as the cosmic microwave background, nearly uniform, yet flecked with tiny ripples, seeds of all future structure. Those subtle imperfections became gravitational starting points where matter clumped, a blueprint for galaxies, stars, and planets. Key points. Big Bang began space, time, energy. Cooling formed first atoms. The CMB preserves the universe's earliest light and tiny seeds of structure. After the universe became transparent, it entered the cosmic dark ages. Light could travel, but no new sources had yet ignited. Vast clouds of neutral hydrogen and helium slowly fell into the slightest overdensities. Gravity was patient and relentless. As clumps merged and collapsed, core pressure and temperature soared until nuclear fusion ignited. The first stars were born, ending the Dark Ages. Population 3 stars, forged from pure hydrogen and helium, were colossal. Hundreds of solar masses, blazing millions of times brighter, but short-lived. They practiced cosmic alchemy, fusing hydrogen into helium, then into carbon, oxygen, and up to iron in their cores. When fuel ran out, cores collapsed and rebounded as supernovae, explosions so bright they could outshine a galaxy, scattering heavy elements across space. Those ashes seeded clouds for new stars and planets. The universe grew richer, with the elements that would build rocks, worlds, and life. Every atom of carbon in your body, the oxygen you breathe, and the iron in your blood was forged in long-dead stars and flung across the cosmos. Key points. First stars formed by gravity. Supernovae created heavy elements. We are literally stardust. With successive generations of stars, gravity, the universe's master architect, shaped matter into ever grander structures. Stars, gas, dust, and dark matter gathered into gravitationally bound systems, galaxies. Early galaxies were small and irregular, but grew through collision and merger into the diverse forms we see today. Spiral galaxies like the Milky Way and Andromeda boast bright arms and glowing gas. Ellipticals house older, redder stars. Irregulars lack a distinct shape, often disturbed by gravity. Our Milky Way is a vast spinning disk with 400 billion stars. We orbit in a spiral arm, 2/3 of the way out, around a supermassive black hole of over 4 million suns. The galaxy is dynamic, constantly forming stars from reservoirs of gas and dust. Galaxies organize into groups, clusters, and superclusters. The Milky Way sits in the local group, within the larger Virgo supercluster. These structures interconnect as a vast cosmic web, grown from tiny early ripples, magnified by gravity over 13.8 billion years. Key points: galaxies assemble via gravity and mergers. The Milky Way is typical. Large-scale structure forms the cosmic web. Second and third generation stars formed from enriched clouds and were surrounded by rotating disks of gas and dust. Within these disks, tiny dust grains, often ice-coated, stuck together. Through accretion, clumps grew into planetesimals. Over millions of years, collisions built protoplanets, whose gravity cleared their orbits and formed mature planetary systems. Around an ordinary star, our Sun, a special world formed at just the right distance. Not too hot, not too cold. Earth could keep liquid water at its surface. The habitable zone matters for life as we know it. Earth's heavy elements came from ancient stars, providing carbon, nitrogen, oxygen, phosphorus, all stirred into vast oceans. Roughly 4 billion years ago, simple compounds self-organized. Somehow a molecule emerged that could copy itself, replication, marking life's dawn. Single-celled organisms akin to bacteria ruled for billions of years, slowly oxygenating the atmosphere in the Great Oxidation Event. Life diversified, multicellular organisms appeared, body plans exploded, and plants and animals colonized land. Humans arrived astonishingly late. Homo sapiens has existed only a few 100,000 years, a blink in the cosmic 13.8 billion year story. Yet we developed consciousness, language, technology, and a curiosity to understand our place in the cosmos. Well, you know, that's where our story begins. Key points: planets grow in disks. Earth's chemistry came from stars. Life evolved over deep time. As measurements improved, astronomers found a startling discrepancy. Outer stars and galaxies were moving too fast to be held by visible matter alone. If only stars, gas, and dust were present, outer stars should slow or escape. Yet galaxies held together, as if an unseen mass provided extra gravity. We call this mysterious substance dark matter. Dark because it neither emits nor reflects light, and is invisible to telescopes. We infer dark matter from gravity's effects, galaxy rotations, cluster motions, and the bending of light known as gravitational lensing. Visible matter is only about 5% of cosmic content. Dark matter accounts for roughly 27% and shapes large-scale structure. It is the invisible scaffolding upon which galaxies form, growing from the earliest density fluctuations. It's not protons, neutrons, or electrons. Candidates include WIMPs and axions. Enormous shielded detectors search for a faint signal. So far, none. Despite decades of effort, dark matter's identity remains one of science's greatest unsolved mysteries. Key points: galaxies spin too fast for visible matter. Dark matter is invisible but mapped by gravity. It sculpts the cosmic web. Its nature is unknown. In the 1990s, teams used Type Ia supernovae to chart cosmic expansion. Instead of slowing, the universe was accelerating. The discovery shocked cosmology and won a Nobel Prize. A repulsive influence must push space apart. We call it dark energy, about 68% of the universe's energy density, and it dominates cosmic fate. Leading ideas: Einstein's cosmological constant, vacuum energy with negative pressure, or a dynamic field that evolves over time. Key points: the universe's expansion accelerates. Dark energy drives it. Its true nature is a profound open question. The cosmic endgame depends on dark energy's behavior versus gravity. 3 scenarios frame the possibilities. Big Crunch. If gravity wins, expansion stops and reverses, collapsing into a hot, dense finale. With acceleration discovered, this is unlikely. Big Rip. If dark energy grows stronger, it could overcome all binding forces, from superclusters to galaxies, star systems, planets, and even atoms. Heat Death. Big Freeze. If dark energy stays constant, expansion accelerates forever. Galaxies drift beyond view. The universe cools, darkens, and empties. Key points. Big Crunch unlikely now. Big Rip needs strengthening dark energy. Most consistent with data. A slow heat death. For trillion-year spans, stars shine as gas and dust dwindle or diffuse. Star formation eventually ceases. The last stars, small dim red dwarfs, live for trillions of years, then fade into cold embers. The degenerate era dawns, skies dotted only with white dwarfs, neutron stars, and black holes. Over longer timescales, planets are stripped from orbits. Stellar remnants are ejected into deep darkness. On timescales of googles of years, a 1 with 100 zeros, even protons may decay, dissolving matter into a thin bath of particles and radiation. Black holes slowly evaporate through Hawking radiation, vanishing in a final faint flash after unimaginable eons. What remains? An almost perfect vacuum, vast and cold, approaching absolute zero. A uniform sea of low-energy photons, neutrinos, and sparse particles. All organized structures are gone. With no processes to mark it, time itself loses meaning. This is maximum entropy, no usable energy. And yet, for a fleeting moment on a tiny planet, we looked up and pieced together this epic story. We are made of exploded stars, and we built tools and minds to comprehend it. Our curiosity compels us to keep looking, keep questioning, and keep telling the greatest story of all.